So far, we've looked at how to find the derivatives of polynomial functions. We've looked at radical functions. We've looked at rational functions. Um, Absolute value functions basically are lines, which are kind of polynomials, so we can take the derivative anywhere but at the point where they turn, because at that point the derivative doesn't exist because we've got a pointy bit. But we haven't yet looked at another huge category of functions. We've sort of been avoiding those. So let's take a look at the derivatives of trigonometric functions. So there are two really important ones to know. And if you've got these two memorized, you can derive all the rest. Okay? Derivatives of sine x and cos x. So these are your two big important ones to have memorized, and yes, you do need to memorize these. So the derivative of sine x dx is equal to cosine x. Wow, that's really interesting. And the derivative of cosine x dx is equal to negative sine x. So, two derivatives to memorize. They're not hard, it's the other one. So the only thing you got to remember is that the derivative of cosine is negative sine. Okay, so now that we have trigonometric functions, we can do a whole lot more when it comes to derivatives. So let's look at an example. So we have f of x equals x sine x. We have a product of two functions here, so we have x sine x, so we need to use the product rule. Okay, so just going to write it out for this one. I may not write it down. So f of x is x, f prime, let's call it g just to make sure we don't get confused with our original f. So g of x is x, g prime of x is 1, h of x is sine x, h prime of x is cos x. Our product rule says it's g prime h plus h prime g. So this is equal to f prime of x is going to be equal to 1 times sine x plus x times cosine x. Okay, which is just sine x plus x cos x. Nothing more we need to do to simplify, not a whole lot we can do. Okay, so let's look at example number 2. We have y equals 2 cosine x, and we're going to find dy dx, but we're going to actually evaluate it at x equals pi over 2. So dy dx is equal to, notice when I use the f of x notation, I like to write f prime. When I'm using a y notation, I generally write dy dx. I'm also really clear that I've got, as in previous lessons, where I'm equal to y and where I'm equal to dy dx. You can't just write an equal sign and then give the derivative, because the derivative is not equal to y. So this is going to be the derivative of cosine x is negative sine x. So the derivative here is negative 2 sine x. Now we are going to evaluate this at x equals pi over 2. So dy dx evaluated at pi over 2, x equals pi over 2, gives us negative 2 times sine pi over 2. Well, what is sine pi over 2? Sine pi over 2 is 1. So this is negative 2 times 1, which is just negative 2. So what does this mean? This means, actually, let's just look at a quick graphical interpretation, that we have a 2 cosine x, so we have a cosine graph with an amplitude of 2. And our cosine graph is coming down. It's coming down to here, and it's coming over here and back up. And you may remember that the first place that we hit 0 on a cosine graph, this is a regular cosine graph, no horizontal stretches, or as we like to call them, no, what do we call them for trig? You know what? I have forgotten. Let's just go ahead and call it a horizontal expansion. So we notice that since there's no horizontal expansions, this is 2 pi, this is pi right here, this is 2 pi where cosine gets back up to the top because we are in cosine, not in sine. And this right here at -1 is pi, which makes this 3 pi over 2. And this is pi over 2. So it's sort of almost the steepest section of the graph. And so what that means is that the slope of the line that is tangent to the graph at that point is equal to -2. So let's not lose sight of what it means when we're evaluating the derivative at a specific point. And -2 sine x will give us the value of the derivative at any point. So notice if we were to plug in pi, the derivative would be 0 because sine of pi is 0. And that would give us a flat line, which makes sense when you look at the graph. All right, example number 3. We have y equals cosine x over 1 minus sine x. So nothing we can do about the 1 minus sine x. We unfortunately are going to have to use our quotient rule. Okay, so let's see if we can do this. We've got cosine x. I'm not even going to write it out. The derivative of that is negative sine x. And we have 1 minus sine x. The derivative of 1 is 0. The derivative of negative sine x is going to be negative cosine x. It takes the same time. So this is our derivative of the bottom. That's our derivative of the top. So y prime is going to be equal to low d high. So sine x times 1 minus sine x minus high cosine x d low minus cosine x, square the bottom, 1 minus sine x squared, and there you go. Well, that looks a little messy. Let's see if we can simplify it a little. So we get y prime equals sine x minus sine squared x plus cos squared x. Okay, well, what do I notice here? I have minus sine x. Oh, wait, did I multiply that wrong? Yeah, that was supposed to be a minus sine x. So we have minus sine x plus sine squared x plus cosine squared x. Well, isn't that lovely? What is sine squared x? And then we've got all of that over 1 minus sine x squared. And we can expand the brackets down below, but I'm not going to do that just yet because I do notice one of my very favorite identities sticking out at me, which is I got a sine squared plus a cosine squared. And so what I'm going to do is I've got y prime equals, this is just 1. So I'm going to rewrite this as 1 minus sine x. I get 1 minus sine x over 1 minus sine x squared. Well, I can cancel one of those. And I get y prime equals 1 over 1 minus sine x. And we can see in this case the derivative actually doesn't exist in the same place as the function doesn't exist because we have the same denominator here. All right, so we're going to do one last one, and hopefully this one will show you that I've given you the derivative of sine x and the derivative of cosine x. But from these, you can get the derivatives and you can derive the derivatives of all of your basic trig functions and their reciprocals. So we're going to do the derivative of tangent of x, but you can just as easily go through and using the quotient rule do the derivative of secant, the derivative of cosecant, and the derivative of cotangent because the technique is the same, just using our quotient rule. So the derivative of tan x dx is equal to the derivative of sine x over cosine x dx. Okay, so what is that equal to? Well, we have low cosine x d high, which is negative sine x, d, which is also cosine x, low d high minus sine x d low, negative sine x, square the bottom. We're going to write it as cosine squared x, and there you go. So now we have cos squared x, minus times minus is plus sine squared x. Well, would you look at that? Isn't that lovely? All over cos squared x. Now, next step, do not tell me it's to cancel the cosine squared x's, because just don't. We've got cosine squared plus sine squared, which gives us our lovely Pythagorean identity. So that is just 1 over cosine squared of x, which can give us secant squared of x. Now, as you can see, we can derive this. It's fairly easy to derive. However, if you wanted to memorize that the derivative of tan x is secant squared x, that might make your calculations faster if you wind up with a tangent in something you're trying to take the derivative of. So whether or not you memorize the reciprocal functions and tangent, up to you if you'd like to memorize those derivatives. It can make things faster, but you're in a pinch, you can always figure them out on your own.